Privyat. Well, that's the way we say hello in Russia. Hello, children. How are you people doing? I'm Sourabh Kumar Dutt, and I'm here to teach you people a little bit of mathematics. Now, children, this lovely place that you get to see is actually the Lake Baikal, which is in Siberia, Russia. It's an awesome place to be in because this is the largest freshwater lake in volume. It is the deepest lake. It is 25 million years old. It has 330 rivers which are flowing into it. However, there is just one river, the Angara River, which is flowing out of it. Further, it has 2,500 species of flora and fauna which are there in it, in which two-thirds of it is to be found nowhere else around the world. Isn't that magnificent? Yes, it is. So do visit this place, and I'm sure you're really going to like this place. However, all the people of Russia that you go and meet there, do say to them, Privyat. In this note, children, I'm going to start off this lecture of binary operations, where we talk about this topic to be a part of relations and functions, which is your first chapter of class 12. Now here, guys, when we talk about binary operations, we primarily first talk about operations. So the first thing that today I'm going to tell you people is about what an operation is. Whenever mathematically we want to get to a result, there is an expression which is required, which manipulates the operands using certain operators, and that then is a mathematical operation. Now here, children, let us talk about a mathematical operation for that matter. If, say, we talk about some y to be equal to x plus 7, right, times of e raised to the power sine x whole upon log of 4x cube, right, and which, say, is whole raised to the power 1 upon 7. Then this is a mathematical operation. Obviously, this is complex, but you can call this to be the operation using the operand, which is x here, right? And after we keep the value of this operand, and also we keep the operators like the plus sign, the raised to the power 1 upon 7, sine x, e raised to the power a number, and log of a number, all of this will be said to be an operation. Right. Further now, guys, whenever we talk about an operation, we require a specific number of operands. And here, when we talk about the number of operands, choosing a specific number of operands is known as the arity. Right. Now, when we talk about the arity, that is the number of operands which are required for an operation, we have different type of operations. That is, if we talk about when there is just no number of operands which are required, it is known as a nullity. Right? For that matter, if you talk about a constant function, as there is no operand which is required, because the constant function will remain to be what it is, and thus it is known as a nullity. Right? So here we will be talking about zero number of operands which are required. Next now, guys, we talk about a unary operation. So if here you talk about finding the fourth root, or probably finding out the square of a number, all of these are known as unary operations, as here you require one operand. Further, we talk about now the binary operation, which will primarily be what we are going to discuss in this lecture. So in the binary operation, we require two operands, right? Further, there can be a ternary operator which requires 3 operands, right, and so on, the list goes on, right? And if you talk about n number of operands which are required, then that, guys, is known as whatever you keep n, like penta, hexa, etc., right? And then after that you add the suffix, which is ari, right? So obviously this will require n number of operands to operate the operation, right? So all of this that I told you people, I'm going to quickly revise with you people. Here, guys, we have an operation which is y is equal to x plus 7 times of e raised to the power sine x divided by log of 4x cube whole raised to the power 1 upon 7. It's a complicated one, but this is what an operation is, where you keep different operands like x here, and then you have different operators like, if you talk about here, e raised to the power sine x whole raised to the power 1 upon 7, etc., right, which are the different operations to be performed, after which you get to the final operation, which is this y is equal to all of this, right? Now guys, whenever we talk about an operation, you require a specific number of operands. If you talk about this process of choosing the number of operands, then it is known as arity. For that matter, if no operands are required, like in a constant function, it is known as a nullity. If it's one operand which is required, it's a unary operation, like finding out the square root, etc. If you talk about a binary operation like addition, subtraction, etc., so this operation requires two operands, and as such it is known as a binary operation. Further, when you require three operands, it's a ternary operation. Then we talk about so on different number of operands which are required. As such, if there are n number of operands which are required, it is known as a n-ary operation. Now n obviously will stand for as many number of operands you're going to keep. Like if you keep 6, it'll be known as a hexa, and then you will add a ary to it, right? And that will be the type of operation it will be. Now guys, here we are going to talk about binary operations. Now, like I told you, when we talk about binary operations, if you talk about operations as simple as addition, subtraction, multiplication, division, which require two operands, right, will all be known as binary operations. Now here guys, after we know what a binary operation is, we are not going to talk about as simple operations as these. We will now be talking about an operation which is a binary operation. That means it will be requiring two operands, and the operation is now as it is next. So guys, this is the operation that we are going to talk about, right? And here guys, if you see, you get to see that this is an operation which is on the Cartesian product n cross n, right? And here, if we talk about the definition of this, the definition goes as, if there are two ordered pairs a comma b and c comma d, right? So this is the first operand, this is the second operand, and when you talk about this binary operation, we are representing this by asterisk, right? And then the binary operation here is the sum of the first elements of the two ordered pairs, right? And the next element of the ordered pair is the product of the second elements of both the ordered pairs. So this is how this binary operation is going to look like. Now here guys, if we're going to talk about this asterisk to be a binary operation, which is the first part, we have to talk about the closure property, right? And further then, we also have to check whether this binary operation is commutative, associative, and we also have to check for identity and inverse, right? So now children, we go ahead with this binary operation and check for the closure property. That is, if the closure property exists, then this is a binary operation, otherwise not. Obviously, this can occur as which will give you a result, but it'll be a binary operation only if the closure property exists. So now guys, let's quickly look up what the closure property is. So if we talk about the closure property, remember this, that if suppose we talk about a binary operation to be, say, a simple asterisk, like suppose if we talk about some a asterisk b, right, which gives us the result to be c, right? And then further, if you talk about all of these elements from where you're choosing your operands, they are part of a set A, then this result c also should be part of that set A, right? So here we should have A, B, C all to be from an element A. If such is the case, then we say that the closure property has been followed, and this operation, which is the binary operation, is having the closure property. As such, it gives you a result, and it is also to be considered to be a binary operation, right? So I'll just quickly repeat what all I said. I said just now that if you talk about the closure property, then let's say we talk about a binary operation which is A asterisk B, which after the operation yields a result C, right? And if A, B, C are all from the set A, which is a replacement set, right, from which we choose these values. So all of these, if they are part of the same set A, then we say that the closure property has been followed, right? And then when the closure property has been followed, we will further be able to say that it's a binary operation, otherwise not, right? So now guys, with regard to this question that is there, we will now be looking up whether this is a binary operation, and now you know that this can only happen if the closure property exists. Okay. Now guys, we talk about this operation here, and we check for this operation. We have here A comma B asterisk C comma D, which gives us the sum of the first elements as the first element of the ordered pair, and the product of the second elements as the second element of the ordered pair, which is the resultant ordered pair. Now here guys, in accordance with what we have discussed, is as here the elements of this ordered pair, that is A, B and C, D, are all elements of natural numbers. So this result which has come, that is A plus C and B into D, also should be from the set of natural numbers. If it is so, then the closure property has been followed. Now let's discuss it out. So here guys, if we talk about A plus C, right, A plus C will be an element of natural numbers, since we say that A comma C are element of natural numbers by the closure property which exists in the sum of the addition of natural numbers. So by closure property, which at the moment I'm abbreviating as C, right, property of addition in natural numbers, right? Obviously the natural number set is known as capital N, right? So in the natural number set that is capital N, as if you talk about the sum of two numbers, it comes out to be a natural number. As such, the closure property is followed there, and as the closure property is followed, so obviously if you talk about the elements of these ordered pairs, even there the closure property is going to be followed. Right guys, now after this we come to the second point. Now we're going to discuss about B into D, right? So if you talk about B into D here, you know that if B and D both are from the set of natural numbers, the product also is going to be from the set of natural numbers. That is, we will say that since B and D are element of natural numbers, right, therefore by the closure property which is there in the product of natural numbers, right, we have this, that this number B into D is also going to be from the set of natural numbers, right? That is, B into D is an element of natural numbers, right? And thus we can say that the closure property is there for this product B into T, and thus we get to see that if we talk about this A plus C, it is an element of natural numbers. If we talk about B into D, it is also an element of natural numbers, and thus both the ordered pair elements are from the set of natural numbers. As such, the closure property is followed, and thus this is a binary operation. Now guys, I'll quickly discuss it out. Here, whenever we talk about the closure property, it is that the product of the elements should be such that whatever you get the result as the product, the initial elements which have been multiplied to get the product, and the product all should be from the same set. And if they're all from the same set, we can say this, that AB being from the set capital A, C is also from the set capital A, and if such is the case, the closure property is followed, and then we talk about this asterisk operation to be a binary operation. Now here, when we are checking with respect to A comma B asterisk C comma D, we have it in accordance with the definition as the sum of the first elements, that is A plus C, and the product of the second elements as the second element of the ordered pair. So if we are able to show that as A, B, C, D are from the set of natural numbers, A plus C and B into D also comes to be from the set of natural numbers, then the closure property has been followed. As such, this is a binary operation. So this is what we are required to show. Now here, the first statement is to be for A plus C. We see that A plus C, which is actually the sum of two natural numbers by the addition property of natural numbers, is to be again from the set of natural numbers. As such, A plus C is an element of natural numbers. Now if we talk about B into D, we know that the product of B, which is from the set of natural numbers, and D, which is from the set of natural numbers, will also be from the set of natural numbers. As such, we talk about the multiplication of numbers in natural numbers, which shows the closure property. As such, here both these elements A plus C and BD show this, that they are from the set of natural numbers. As such, the closure property has been followed, and thus this binary operation that we are doing shows that it has the closure property in it. Now guys, after this, we will now be moving towards the next property that we've got to check for, that is the commutator property. Right now, after this guys, when we talk about the commutator property, we will go ahead with the basic definition of the commutator property. Now in the commutator property guys, we will first talk about the basic definition. Let's say if we talk about some binary operation A asterisk B, if that comes to B asterisk A to be the binary operation, then it shows the commutator property. Now with regards to this operation that we have, if say we talk about a ordered pair which is A comma B, and then let's say there be the binary operation with another ordered pair which is say some C comma D, then we get it to be A plus C comma B into D, right, which is after the binary operation has been done. So here guys, if we can show that changing the order of the elements, if we can get to the same result, then we will say that this is a commutator property following binary operation, otherwise not, right? So here, as you see, first it is when A comma B comes first and C comma D comes next. Now if we talk about C comma D to be coming first and A comma B to be coming next, then obviously it should be C comma D asterisk A comma B that we should be talking about. And if we talk so, then obviously the first elements will get added. As such, we will have C plus A, and then we will talk about D into B, which will be the product of the second elements of both the ordered pairs, which will now give us the resultant ordered pair. Now we are to check if we find that the first element has matched the first element and the second element has matched the second element, then obviously we can say that if we do the binary operation by changing the order of the elements, the result remains to be the same, then we will say that this binary operation is showing the commutator property, otherwise not. Now let's go ahead and check for it. So guys, as we know that if we talk about A plus C, that is equal to C plus A, as the commutator property exists for the set of natural numbers, rather for addition in natural numbers, right? And thus guys, we can say that this is perfectly true. Now after this, if we go ahead with the next thing, that is if we talk about the product elements, now we've got to show that if we talk about the other, that is B into D, it should be equal to D into B. And again, this is perfectly fine, as if you talk about the commutative property, then the commutative property exists for the multiplication in the set of natural numbers, right? And as such, here we say that this is perfectly true, that B into D is equal to D into B. And since both of the elements are coming to be exactly the same, whether you keep the first element, that is the first ordered pair first, or the second ordered pair first in finding out the binary operation, therefore you can say that indeed this is commutative, right? Now guys, I will quickly discuss this again with you people, so that if there is any cloud of ambiguity which is there, right, then all of that gets dissociated. So I'll just quickly discuss this all over. Here guys, we are talking about the commutative property. So basically what commutative property is, I discuss first. That is, if you talk about A asterisk B, that is A binary operation B, if that comes to be equal to B binary operation A, then we say that this is a commutative property exhibiting binary operation. Now here, as the binary operation is A comma B asterisk C comma D in ordered pairs to be the sum of the first elements comma the product of the second elements. So here, if we reverse the order by keeping C comma D to be the first ordered pair and A comma B to be the second ordered pair, and even then if the result comes to be the same, then we will say that this is a commutative property following binary operation. Now guys, first we talk about A plus C to be equal to C plus A, because if you talk about this, this is just the addition of two natural numbers, and since the addition of natural numbers is commutative, right, we already know it as we've dealt with natural numbers earlier, right? So we know that this is true, therefore the first element of the ordered pairs are equal. Now we talk about the second elements, as in the second elements we have B into D, which obviously is going to be D into B, as the commutative property exists in the multiplication natural numbers, and thus we can say that both of these elements are exactly the same, and thus if you keep the first ordered pair to be first or the second ordered pair to be first in doing the binary operation, the result comes out to be the same. As such, it is commutative property following binary operation, right? Now after this guys, we will be talking about the associative property. Now when we talk about the associative property, then remember guys, first we'll be talking about the basic property, and then with regards to this given question, we will then be discussing whether it's a associative property following binary operation or not, right? So here guys, when we talk about the associative property with regards to the normal binary operation, so if we talk about say some A asterisk B asterisk C, where A asterisk B is considered first to be equal to A asterisk B asterisk C, where B asterisk C is considered first, if both of these sides of this equation are equal, then we say that the associative property is followed, right? Now guys, we will talk with respect to this operation that we have here at hand. So if we talk about now A comma B to be the first ordered pair, C comma D to be the second ordered pair, and let us consider E comma F to be the third ordered pair, where when we talk about the binary operation, we will first be doing the binary operation of the first with the second, and then after we get the result, we will do the binary operation with the third. And on the other side, we will now talk about here again the first ordered pair A comma B, the second ordered pair C comma D, and the third ordered pair E comma F. Now we're going to perform the binary operations with the second and the third first, and whatever be the result with that, then we are going to operate with the first ordered pair. So let's go ahead and do this. So here further, when we talk about A comma B asterisk C comma D, that is this binary operation, we'll have the sum of the first elements as A comma C, A plus C, and the second elements to be multiplied together, that is B into D, right? And further here, if you talk about, this is going to be the resultant ordered pair. And now we're going to talk about the binary operation it has with E and F. That will give you the sum of the first elements, that is A plus C, which is the first element of the first ordered pair, added to the first element of the next ordered pair, that is E. And now we will have the product of the second elements of both the ordered pairs, that is B, D, F. Now this will give you the resultant ordered pair. Now let's come over to the right hand side and give a try as to what is going to happen. So first, guys, we'll be talking about the second and the third ordered pairs, where we'll talk about the binary operations first. So here we have C plus E comma D into F, which is going to be the resultant ordered pair in accordance with what binary operation we have at hand. Now guys, we are going to operate both of these ordered pairs. As such, it is going to give us A plus C plus E, which is the first element of both of these ordered pairs. And now if we talk about the second elements, there is going to be a multiplication, so we will have B, D, F. Right, so this, guys, is the resultant ordered pair on the right hand side. And now we try and compare with the elements of both the sides. We find that if we talk about A plus C plus E, it is exactly the same as A plus C plus E. And if we talk about B into D into F, it is exactly the same as B into D into F. And here we also require to write, since A, C, E are here the elements of natural numbers, as such they exhibit the associative property with regards to addition, right? So this is what we are going to write here, that is, since A comma C comma E are element of natural numbers, therefore they show the associative property with regards to the addition, right? That is, if you add to A plus CE, or if you add to C plus EA, both are going to give you the same result, right? And this is why you have this here. And next, then we'll be talking about the next thing, that is, when we talk about the product, we will have B comma D comma F, which are all element of natural numbers, therefore they show this property, the associated property with regards to multiplication, right? And as when they are multiplied together, then whether to the product of the first and the second, the third is multiplied, or whether to the product of the second and the third, the first is multiplied, it again remains to be the same. As such, the associated property exists with regards to multiplication of natural numbers, and thus we can say that both the sides have the same ordered pairs with the exact same elements, right? And thus here we have the associated property which exists, right? So this is what we have for this binary operation. That is, till now we have checked up for the closure property, we have checked up for the commutative property, and we also have checked up for the associated property. Now guys, after this we are now going to talk about the identity element. And remember here, once when a binary operation has an identity element, only then we can talk about its inverse. Why this happens is what is going to get clear after we talk about the definition of identity and inverse, right? For that matter, guys, here now we are going to talk about the identity. Now, when we talk about the identity element, then in the identity element here, we require, by the definition, such an element such that if we talk about the identity element to be, say, some E, then A binary operation E should be equal to E binary operation A, which should further become equal to the original element, that is A, right? And now, guys, in accordance with the operation that we have at hand, if, say, we talk about A comma B to be the first ordered pair, and let us now talk about the identity element to be, say, some E1 comma E2, right? Then if we perform this in the reverse order, that is, here we have E1 comma E2 to be the first element with which we perform the identity operator with A comma B, and again if it gives you the same ordered pair A comma B, then we say that here we have E1 comma E2 to be the identity element, right? This is by the definition. Now, guys, here we will try it out as to what is going to happen in accordance with the definition that we have at hand. So here, if we talk about with regards to this operation, the binary operation, then if you talk about A comma B binary operation E1 comma E2, then the first element, guys, is going to become the sum of the first elements, that is A plus E1. And if you talk about the second elements, then it is going to become equal to B times of E2. And further, that should be the same as E1 plus A, that is the sum of the first elements, comma the product of the second elements, that is E2 into B, right? And both of these are the two elements of this ordered pair. After this, now, guys, we will now be talking about the actual ordered pair that we had initially, that is A comma B. And thus, guys, if we talk about here A plus E1, it should be equal to E plus A1, and that should become equal to A. And as you know, by the addition of natural numbers, or for that matter the addition of numbers, we know that 0 is such a number which, when it is added to a number, it gives you the same number, whether you add it from the right hand side or whether you add it from the left hand side. That is, whether you perform the left hand addition or whether you perform the right hand addition, it should give you the same element A, and that is only possible if we talk about this E1 to be 0. So here, if we talk about this E1, it should become equal to 0, and since you know that E1, that is 0, is not an element of natural numbers, therefore the identity won't occur. And here you will state this, that since 0 is not an element of natural numbers, therefore as the first element is not equal to the first element, right? So therefore we can say that no identity in this operation, right? So as you do not have an identity element, right, therefore you won't be able to talk about inverse, which in times to come I'll be discussing how both of these are so much linked together. Now here, guys, we'll be talking about the identity element. If you talk about the identity element, we talk about A asterisk E to be equal to E asterisk A, which is further equal to A, and this is what the definition is. That is, if you perform the identity operation, if you perform the binary operation with the identity element, then you should get the initial element, that is A, right? Now here, guys, when we perform this operation, considering that E1 comma E2 is the identity operator here, so obviously after performing the operation, be it from the left hand side or be it from the right hand side, it should give you the original ordered pair. And as such, in accordance with this operation which we have at hand, A plus E1 is what the first elements will become, right, as we'll have the sum of the first two elements of both the ordered pairs, and then we'll talk about the product of the second elements of the ordered pairs to be the second element. And now when we talk about the left hand operation, if we talk about E1 plus A, that will become the first element, and E2 into B will become the second element. So here, if you talk about the operation resulting into the first element to be the same as the original ordered pair A comma B, that can only happen, guys, if A plus E1 is equal to E1 plus A is equal to A, and that is possible if the value of E1 is 0. So as 0 is not part of the natural number set because it starts from 1 and goes up to positive infinity, like 1, 2, 3, 4 and so on up to infinity. So therefore we will say that there is no identity element with regards to the first element of the ordered pairs. Now if we talk about with regards to the second element of the ordered pairs, then let's quickly check what will happen here. So if you talk about BE2, right, then BE2 is equal to E2B, which is equal to B. Now this is possible if you have the value of E2 to be equal to 1, and as 1 is an element of natural numbers, so obviously this is perfectly possible, right? But since the first element of the ordered pairs has not shown identity, therefore we will say that the identity element with regards to this binary operation of ordered pairs doesn't exist. Right now, guys, after this we will now be talking about the next thing, that is we will now be talking about the inverse operation, right? So let's first look up what the inverse operation is, and then I will tell you its close relation with the identity element. So guys, here if we talk about the inverse operation, then the inverse operation or the binary operation having an inverse is possible if we talk about it with respect to the definition. That is, if you have an element A which is binary operated by another element which say is its inverse, let us consider that to be say some F, then that should be equal to F binary operation A, and that should give you the identity element, which here earlier we've considered as E, right? As such, this should give you the identity element E, right? So as in the last step we have considered the identity element to be E, as such here also I'm writing the identity element to be E, right? Now guys, here with regards to this operation that we are doing, we have ordered pair of A comma B, and if say we are to perform a binary operation with the inverse of this ordered pair, then that has to be say some F1 comma F2 which say is the inverse, right? Then obviously this should be equal to F1 comma F2 binary operation with the initial ordered pair, that is A comma B, and this, guys, should give you the identity element, that in this case, like we've discussed in the last case, if it is E1 comma E2, then this should give you E1 comma E2. I'm sure now you have been able to understand this, that if we do not have this E1 comma E2, which is what after the identity operation you check for the result, then how is it that you will be able to talk for the inverse of this binary operation, right? As such, if you talk about the inverse of a binary operation, the identity element is quintessential to be existent, right? I'll just explain all over again. Now here, guys, in this question we've got to find out whether this binary operation, that is A asterisk B, has an inverse element. For that, we first talk about what the basic definition of inverse element is. That is, if you talk about A asterisk F, then that should be equal to F asterisk A, and that should further be equal to E, which is the identity element. Here, guys, we have considered that this F is actually the inverse element of A and E is the identity element. So as when we are talking about the definition, we are primarily talking about getting the result of doing the inverse operation with the initial element A to be the identity element. Thus, if the identity element is not existent, how will you be able to check whether the operation has an inverse or not, because identity element's existence is quintessential, right? So here, with regards to the operation that we have at hand, we will quickly check. If we talk about a comma b asterisk f1 comma f2, which here asterisk here is the binary operation, obviously that should be equal to the other way around, that is f1 comma f2 asterisk a comma b, that is binary operation a comma b, which should give you the identity element, which is e1 comma e2, which has been considered here in the last case. So as here we find that the identity doesn't exist, therefore the inverse also won't exist, and this, guys, is what we're going to write here. You will say that since the identity operator does not exist for the binary operation asterisk, therefore no inverse will exist for any element of n cross n, because we are choosing all the elements from n cross s, n cross n. As such, there won't be any inverse in this set. Okay, guys, now all of this that we had, all of this has been discussed clearly, and I'm sure all of this you have been able to understand very well, right? And any doubt that you have here, right, you require to give me a message again, and I'm sure to get back to you so that I can explain more. And I'm sure you people must have understood of how we go ahead with the binary operations, right? And in times to come, if you have the binary operation to perform with different elements, different cases, I'm sure you'll be able to deal with it very well. So do study well, do work hard, because maths without practice doesn't give you any results. So as such, all of this which has been taught to you, make sure that you practice it once more and do try out the sums from your exercise. And if there is any difficulty in any sum that you do face, do give me a message, right? And I'm sure to revert back to you and help you people out. So bye now, and have a nice time and enjoy your lives. Bye.